So today we talk relations, functions, symmetries, and increasing and decreasing intervals. This could be a long one, so buckle up. Relation. Basically, mathematically, a relation is just a situation where one item corresponds to another. You can think of it as like an ordered pair, as stated in the slide. Functions are relations such that for every x there exists a unique y. That means a singular y, unique. Domain is a set of all x's, range is a set of all y's, all things you should have learned in Algebra 1. All right, so when I look at this set of ordered pairs, all right, and I want to define the domain. Domain is basically equal to the set of all x's, so that's 1, 5, and 3. You can put them in order, I don't really care. Range, set of all y's, so that's 2, 8, and 7. And if for some reason a number is listed twice, you only need to list it once. So here I have two relations, all right, one of which is a function, one of which is not, all right? So think to yourself, which one would be your pick? And I'll take a 5-second pause, just do it on real quick. All right, well, if you don't know, here's the best way I find to do these things. Take a look at what they would be on a graph. So I'm just going to take and plot these points. Here's 1, 3-ish, right? 5, 4, 7, 7, 2, 3, right like this. Now, for every x, is there only one y? Well, you check that by drawing vertical lines, and if there's only one dot that it goes through, then it's a function. So this is a function. Likewise, if you graph these guys, 8, 1, somewhere around here, 2, 2, somewhere around here, 5, 3, somewhere around here, 2, 7, somewhere around here. Again, draw a vertical line through all those guys, and you notice this guy fails. It passes 2 points through the same x value, so this is not a function. We call this a vertical line test. Basically states if you can draw a vertical line through any graph or set of points, if that vertical line passes through more than one point, then that picture is not a picture of a function. Function notation. So back in Algebra 1, everything looked like this. Y equals 7x plus 12. And they say, given this function above, find y when x equals 1. And you just took and you shoved that 1 right into that x value, and you said, well, hey, that's just 19 is equal to y. All right, and then for some reason, everybody gets freaked out because we take the y out of the problem, put an f of x in its place. That just says this is a function that is going to be named only in terms of x. There won't be any y's in it. And then they said, given that function, find f of 1. Well, basically what just happened is we took out this x and put a 1 in its place. So we're saying basically x equals 1. And it's the same darn thing, but people freaked out, and I don't know why, but it happens. You know, we get 19 and y, or f of, sorry, almost did it, f of 1 is equal to 19. Same thing, don't freak out. Next. So here's a whole bunch of function evaluations. So here's my function f of x, and I'm going to evaluate these 3 problems given their specific values. So this says basically just like the last problem, shove that 3 right in there. So f of 3 is equal to 2 times 3 minus 3 or 3. F of w plus 4, well, this is taking the place of x. So again, we're just putting it in its place. F of w plus 4 is equal to 2. Instead of x, I have w plus 4 plus 3. So f of w plus 4 is equal to 2w There's 8 and 3, which is 11. All right. Now, this is a little different. It says f of x equals 14. So in this case, they're taking out the whole f of x and putting 14 in its place. And they want to know what x equals. So in this case, bring the 3 over, divide by 2, and 17 over 2 is your x value. This is a little more abstract. Again, we had that f of w plus 4 before. Well, now I've got two variables in here. I have x and delta x. And here's my function, which is a little more complex than the previous function. But again, I'm just taking out an x and replacing it with x plus delta x for every x that I see. So this is x plus delta x squared plus 4x plus delta x minus 3. All right, FOIL, x squared plus 2x delta x plus delta x squared plus 4x plus 4 delta x minus 3. Combine like terms. Yeah, I don't see too many of them right here. In fact, there aren't any. And that is your expression. So, done with function notation. Let's move on to symmetry. So symmetry, from your geometry, you know that symmetry talks about folding something over onto itself and kind of like matching on either side of a line or a point. Okay, so what we have here is we have a line symmetry in this case, and we have a point symmetry in this case. In the case of a line symmetry, the line in which the function is symmetric over basically is a line that perpendicularly bisects the segment dividing the 2 points. So that would be the case in this spot. And then you know that if it's a y-axis symmetry, which this case is talking about, then you have a point of xy. When you flip that over the y-axis, you get a image point, p prime, of negative x and y. All right? And it turns out that any y-axis symmetric function is called an even function. Now, in the case of origin symmetry, that's a point symmetry. We know the origin is at 0, 0. And a point symmetry, if you've got that existing, all right, basically what's going to happen, let's see if I can get a small line going here. If I do this point symmetry, then I connect the two dots, which I'm flipping over, that's supposedly symmetric, and that creates a segment. And the point of symmetry, the origin in this case, would then be the midpoint of that segment of the 2 points that it joins. So if it's an origin symmetric problem, then my point of xy goes to a point over in the third quadrant of negative x, negative y. And we call this kind of a function an odd function. So origin symmetry is an odd function. Y-axis symmetry is an even function. All right. So let's keep it going. If I can find my cursor, which I can't do right now. There we go. All right. So tests for symmetry, and I just kind of outlined them without really stating it in a sentence. So here I am now. In this case, both the opposite of x and y and x and y are on the graph. And to prove it, we substitute an x for, or a negative x, sorry, I should have put that in parentheses, for x, and we get the same resulting equation, where we have a symmetry of the origin case. Both the negative xy and the xy are on the graph, and we substitute a negative x for the x and a negative y for the y, and you get the same resulting equation. All right, and then I guess the question you should be asking right now is, what the heck are you talking about with an equation? Because in the last slide, all you did was show us two graphs and no equations. All right, well, that's coming up. So here's an equation. We want to show that this is symmetric to the y-axis, which means show that this is true. Well, this equation right here is the xy equation. It has a positive x, positive y thrown in. So now if I want to throw the negative xy case out, then I have to replace the x with a negative x. Y stays the same, and I have to show that this equation is the same as my original. Well, negative x squared is x squared, and y is y. And lo and behold, this is the same as this, so therefore, these three little dots in a triangle means therefore, it's y-axis symmetric. If they weren't the same, then it wouldn't be y-axis symmetry. And once again, that y-axis symmetry means it's an even function. So here's another case where I want to show origin symmetry. And in origin symmetry, like I wrote before on the slide, you have to plug a negative x where the x is and negative y where the y is, and show that the starting equation, the xy equation, which this guy is the same as the negative x, negative y equation. So let's make our substitutions. I put a negative y here, put a negative 3 and a negative x for every x that I see. Go ahead and simplify this a little bit. This goes to a negative, and a negative is a positive. This goes to a negative 5x. Sorry, I forgot the cube. And now multiply by a negative 1 to both sides. Negative 3x cubed plus 5x. Hey, there we go. They're exactly the same. So this is origin symmetric and thus odd. Okay, let's start talking about some polynomial functions. Now, this is a polynomial function. Typically, polynomial functions are smooth graphs that fluctuate up and down in curvilinear fashion. It's a fancy word, all right? But within this graph, we're going to notice a couple of points. There's a little hill right here and a little valley right here. Hills and valleys create what are known as maximum and minimum points. And in this case, we call this a relative maximum because this graph actually goes higher. And we call this a relative minimum because this function actually goes lower, all right? So if you look at a graph like this, put arrows on this guy, this is a maximum, as is this a maximum. However, since this isn't the biggest maximum, we call it a relative, and this is the biggest minimum, so we call this an absolute minimum, all right? And since this goes down forever, this will never have an absolute minimum, but it can have this relative minimum at the valley, if that makes any kind of sense to you. So now here's another graph where I've got some things labeled. And we want to define or state increasing and decreasing intervals. Remember, these are in terms of x's, x intervals. So where does this increase and decrease? Let's start with that. And we're going to do this in interval notation. So I look for where it increases. That means where does it go up? Well, it goes up from the x value of negative 1.25 to the x value of 0.01. Or 0.1, sorry. And we're going to say those aren't inclusive. There's a little bit of argument in the calculus world where you say they are and they aren't, but I'll let the calculus teacher deal with it. I'm going to say at that point it neither increases or decreases because it looks like it levels off. All right. And then this also increases from this x value, which is 1.5, and it goes up forever. So since it goes up forever, that means is the further I go out, the more it goes up. So this goes to infinity. Remember, these are x values in interval notation. These are not points. Now, where's it decrease? Well, it decreases, notice as my pencil or my cursor goes through this curve, it's going down. So it decreases from negative infinity to that x point of negative 1.5. and now it goes up here, and now it drops again here. So from 0.1 to 1.5, it's also going down, and that's where it decreases. Now, where are the maximum and minimum values? Or better yet, what are the maximum and minimum values? We say this has a relative max of, well, this is a relative max right here, and we're going to use the y value to state what that relative maximum is. Now we have two, or actually we have an absolute min at negative 3.2 and a relative min at negative 0.5. And again, these are all y values. Now, we can state this as follows. We could say rel max of 2.1 at, here's my 2.1, 0.1. This is your y value, this is your x value. But if you tell me there is a relative max of 0.1, I'm going to mark that entirely wrong, because that's not true. You have to state the y value. Okay, now what we're going to do is we're going to need to use our calculators. All right, so get those things fired up and do what I'm going to do with me. So the first thing you're going to want to do is you're going to want to hit y equals. Once you hit y equals, you're going to plug in this formula. All right, the power key is like this. I'm an old school guy, so I use what's called the classic mode. There's a new mode that makes it look exactly like this problem, but again, I'm old school. So once you get that done, you can pause this if you need to. You're going to hit zoom, followed by 6, which is standard. That means it will graph this in a 10 by 10 window. And you'll notice nothing's there right now because it's calculating all the stuff on the other side. Hey, here's something. But it's clear that that is not the equation of a line. All right, there's something else going on. And it looks like it keeps going up, so there's maybe something higher. And I need to see something higher. So what I will do is I will look at my window and adjust that. So if I hit window, I notice that I'm going from negative 10 to 10, as I told my calculator to do by hitting standard. I want to see higher. I don't want to change any of the x values, but I do want to change the y value to a higher value of 30. So I'm going to type in 30, then I'm going to regraph it and see what happens. And here I go graphing again. And sure enough, it did something. Now, it's going up and down, and there's a maximum and minimum right in here, but I can't see it really well right now, and I'd really like to see it better. So I'm going to zoom in on that point. So I'm going to go second. Actually, not second, I lied. I'm just going to go zoom. And I'm going to go Z box, number 1. Now you'll notice that I've got this thing like pointed right in the middle here. If I move it, you will see, hopefully, on your calculator, if not mine, this thing actually blinks. What I want to do is I want to put this little cursor guy up and to the left of my relative maximum. And then I'm going to hit enter. So next, you see that guy's blinking right now. I'm going to bring it down to below my relative minimum. And I've created a side of a rectangle. And now I'm going to drag it to the right. And I'm going to enclose that whole piece of the graph that is interesting to me. And then after I've done that, I'm going to hit enter. And what it does is it zooms in on what I just encircled. So I see I have a relative min and a relative max. You can see the relative max is here, the relative min's right here, but I don't know their values. So I'm going to find their values by saying second calc, and I'm going to find that maximum. So I'm going to hit the number 4. And notice what it says. It says left bound. So I want to take and go to the left of the high point. So I'm going to cursor over. Like so. Hit enter. Then cursor to the right of that high point. Hit enter. And for some reason it says guess. I never know why, but it does. And I hit enter a third time. What it's going to do is it's going to spit out that x and y value. And so what I've done is I've taken and I've drawn a relative, picture of that graph, and I've put in that point right here. Now we have to find this relative minimum, so we're going to do the same thing. We're going to go second, calculate, and instead of finding a maximum, we're going to find this minimum. So I hit 3. There's my blinker guy again. I'm going to put that to the left of the low point, hit enter, put it to the right of the low point, hit enter. Says guess. I'm going to hit enter the third time. And now I've got where this is at its low point. And you'll notice that this time the point's actually in scientific notation. This is 1.3 times 10 to the negative 6th power and 10. So that's basically 0 and 10. Now I can go ahead and answer the question. So it asked me to find the maximum value and the minimum value, rel max at 10.74, rel min 10, state the intervals in which the function increases and decreases, increasing from negative infinity to 0.58, sorry, and from 0 to infinity, and then decreasing from 0.58 to 0, and that's about it. All right, that's all we got today. We got it in under 24 minutes, which is good, so we'll take it. See you next time.